The Industrial Internet of Things, or IIoT in short, has become the main driver of productivity for today's industrial operations. By 2025, IIoT is expected to become a $500 billion market. So what is IoT and why the huge spending on it? IIoT is essentially an interconnected network of devices that delivers intelligent insights. These insights can help reduce downtime in smart factories, adjust transportation routes in logistics, and many more. Needless to say, all these use cases require timely, if not near real-time content access. This is where edge caching comes into play. Edge caching is to store contents temporarily at the edge of the network. With reference to this edge computing model known as multi-access edge computing or MEC, we can see that edge caching allows end users to retrieve certain contents from nearby MEC servers. This reduces latency of content access. But with huge volume of contents generated by IIoT networks, the question is how to effectively and efficiently decide the contents to cache. So here we proposed a distributed deep learning edge caching strategy. The idea behind the proposed strategy was to leverage on the computational power of MEC servers in the network to predict popular contents which end users are most likely to download. And so the aim of my project was to investigate the use of MEC and the proposed strategy to jointly support low latency content access in IoT networks. But first, let's take a brief look at our 5 benchmark strategies. The least recently used and least frequently used strategies evict the least recently and least frequently used contents from the cache when the cache is full. The most popular content simply caches the most frequently used items over a past time period. The oracle strategy is to cache the true most popular contents in the future time period, which is ideal but impractical. The centralized deep learning method is the centralized variant of the proposed strategy. The remote content server collects content demand statistics from the whole network, centrally trains a model and caches the predicted most popular contents. Now for the proposed strategy, a feed-forward neural network with 2 hidden layers and a dropout layer was initialized as the global model. The global model is then sent to the MEC servers, and the MEC servers each execute a complete pass on their local dataset. By the end of the epoch, the weights of the local models will be updated. Then the weights of the global model will be synchronously updated with the weighted average of the local weights. These weights will then be sent back to the MEC servers before the next epoch. After the training is complete, each MEC server makes local predictions using a replica of the trained global model. Before evaluating the strategies, we simulated network data. Empirical studies have shown that web content requests generally conform to this law, which suggests that content popularity is inversely proportional to request frequency. So we randomly generated user requests that follows the ZIS distribution and took content popularity as the content index. The distribution parameter was set to 1.01, so the strict ZIS law can be followed as close as possible. On the right is the graph obtained when there were 1 million user requests generated. The benchmark and proposed strategies were evaluated using 2 key indicators, cache hit rate and real-time latency. Cache hit rate was taken as the number of cache hits divided by the total number of requests made in a network. Under pure simulation settings, the proposed strategy was found to be closest to the optimal strategy, which is the oracle. It was also found to be higher than other strategies. Notably, the increase in cache hit rate over RU and RVU at lower cache sizes is 5 to 10%. Although cache hit rate of the proposed strategy is more or less similar to the most popular content strategy, it can be noted that the MPC performs worse when there is limited input data available. Next, we examined how higher cache hit rates can translate to a reduction in real-time latency. To do this, a prototype of the edge caching system was set up on an edge caching testbed designed for industrial use cases at the Advanced Remanufacturing Technology Center, or ARTC. In this edge caching system, there were 3 simulation environments: a physical laptop for MEC clients, an on-premises virtual machine for MEC servers, and an Azure virtual machine for the remote content server. We also hosted a performance measurement service on the on-premises virtual machine. Here, it can be noted there were no Oracle MEC clients because the Oracle strategy is simply impractical to implement in real life. Instead, we included non-edge caching clients to use as a benchmark. Using the edge caching system, we measured average latency, which is the average time taken for end users to download content. Then we used latency to derive latency improvement, which is the reduction in latency as compared to when no edge caching strategy was used in percentage terms. We can observe that the proposed strategy gave the lowest latency as compared to benchmarks, with a 73% latency improvement at a given cache ratio of 0.1. Overall, judging by the key performance indicators, the proposed strategy was found to be able to satisfy the tight latency requirements of IoT use cases. Nevertheless, modifications can be made to optimize the proposed strategy, such as by making the wait update process more efficient or by reducing redundancies of cached contents among a cluster of MEC servers.